Hey everyone, and welcome back. We flip a switch and the lights just come on. But behind the scenes, there's a whole world of invisible guardians keeping things running. Today, we're diving into one of the most important ones, transformer protection. It's a topic that's absolutely critical, but one you almost never see.
So have you ever wondered what it takes to protect the very heart of our electrical network? Because that's really what a power transformer is, right? It's the beating heart of our entire system, an essential, incredibly expensive, and surprisingly fragile piece of equipment that makes our modern world possible.
All right, so here's the game plan. First, we're going to talk about why these transformers are so vital. Then, we'll get into the anatomy of how they actually fail. After that, we'll explore the two main ways we protect them, kind of the brute force approach, and then the really clever, intelligent one. And finally, we'll look at why putting all this into practice isn't always so simple.
Okay, first up, the transformer's vital role. It is so easy to overlook these big metal boxes, but trust me, without them, the whole power network would just grind to a halt. So a transformer's job sounds pretty simple, right? It just steps voltage way up so we can send electricity over long distances, and then steps it way back down so we can use it in our homes. But that makes it the absolute critical link in the whole chain. If one fails, it's not just a broken part, it's a massive power disruption. And let me tell you, swapping one of these giants out, that's a huge, expensive headache. Now that we know why they're so important, let's look at what we're actually up against. I mean, how does a massive hunk of steel and copper just fail?
Yeah, transformers really live a tough life. Think about it. Every single day, they're physically expanding and contracting as they heat up and cool down. They're constantly vibrating. They get hammered with these huge electrical punches from faults happening somewhere else on the grid. Throw in overheating from high demand and random voltage surges, and you've basically got a device that is under constant assault. And when you look at the data of how they fail, a really clear picture starts to emerge. The number one culprit? The windings. Those are the big copper coils doing all the work. They account for over a third of the problems. And right behind that are tap changers, which are these complex mechanical switches that fine-tune the voltage. So yeah, it's pretty obvious where the weak spots are.
But what's the real villain here? The root cause of all this? Well, in so many cases, it all comes down to one thing: insulation failure. You can think of the insulation as the transformer's immune system, and once that system gets compromised by heat, moisture, or just old age, a catastrophic short circuit is pretty much inevitable.
Okay, so how do we fight back? How do we stop this from happening? Let's start with our first line of defense, overcurrent protection. Honestly, you can think of this as the big, tough security guard at the door. Not subtle, but definitely effective.
And the idea here is super simple. It's basically the same thing as the circuit breaker in your house. If way too much electrical current starts flowing through the transformer for too long, bam, a switch flips, and it cuts the power. It's a fundamental but really solid way to protect against those big, obvious problems, like a major short circuit down the line.
But don't let the simplicity fool you. Where you place this guard is actually really strategic. On the high voltage side, it's set up to be a backup, and it's smart enough not to trip for every little problem happening miles away. Then, on the low voltage side, its job is to act as a safety net, catching any local faults that other devices might have messed. It's all about making sure the right device handles the problem without causing a bigger blackout.
So, overcurrent protection is awesome for dealing with big, obvious brawls happening outside the transformer. But what about an inside job? A fault that's happening deep within the transformer itself. For that, you need a much, much smarter security system.
This is where we get to differential protection, and honestly, the concept is beautiful in its simplicity. It's all based on one of the most basic laws of physics. What goes in must come out. The system is constantly measuring the current flowing into the transformer and comparing it to the current flowing out. If those two numbers don't add up perfectly, the system knows. It knows some of that current has gone missing somewhere. It shouldn't. A dead giveaway of an internal fault.
The absolute best way to think about this is like one of those laser grids you see in a heist movie. There could be a riot happening in the street right outside the bank, and the alarms stay silent. But the very instant a thief breaks a single laser beam inside the vault, the alarms go off immediately. That's differential protection. Okay, so let's walk through a scenario. Let's say a tree falls on a power line, like miles away. A massive amount of current is now flowing through the transformer to feed that fault. But our laser grid? It sees that the same amount of current is flowing in as is flowing out, so it just says, nope,
not my problem, and stays quiet, letting some other device down the line handle it. Okay, but now let's change the scene. What if there's a problem inside the transformer, a short between the windings? All of a sudden, current is gushing in, but it's not all making it out. That imbalance, that's the smoking gun. That's the broken laser beam. The relay sees that difference and trips the breakers in a fraction of a second to isolate the transformer and prevent it from tearing itself apart.
And that's why this method is just so brilliant. It's incredibly fast, which means way less damage to the equipment. It's surgical. It only operates for faults inside its zone, which helps keep the rest of the grid stable. And because it's so specific, it doesn't need to check with anyone else. It sees an internal problem, and it acts. Period.
Okay, so that all sounds pretty perfect, right? Almost too easy. And, well, you'd be right. Because trying to apply this beautiful, elegant theory in the real, messy world, well, that comes with some major headaches that engineers have to solve. See, the protection system has to be smart enough to tell the difference between a real fault and a few common curveballs. For instance, the sensors that measure the current aren't always perfect. The transformer's own wiring can actually shift the timing of the electricity just a little bit. And the big one, just turning a transformer on causes this huge but totally normal spike of current called inrush that looks almost identical to a catastrophic fault.
And this inrush current is a perfect example of how clever these modern systems are. That huge spike of current, it turns out, has a unique electrical fingerprint. It's full of these specific distortions. Engineers call them harmonics. So the relay is basically trained to be a detective. It looks for that specific fingerprint. If it sees a huge current spike, but it also sees that harmonic fingerprint, it knows, this isn't a robbery. The owner is just opening the vault, and it holds back from tripping. It's brilliant. So at the end of the day, when you strip everything else away, the whole philosophy of protecting these critical machines really comes down to these three simple goals. 1. Detect the fault instantly to minimize the damage. 2. Isolate the broken equipment immediately. And 3. Do it all in a way that keeps the rest of the power grid up and running.
And that really brings us to the big question, looking forward. We've just seen the incredible logic that was built to protect the grid we have today. But as our grid gets more complex, with power flowing in all directions from things like solar and wind, how are these silent guardians going to have to evolve to keep protecting the heart of the network? That's the puzzle for the next generation of engineers to solve. Thanks for digging into this with me.